So let me introduce our next speaker. Emily Cliff will be telling us about moduli spaces of principal two-group bundles and a categorification of the Freed-Quinn line bundle.
Thanks, Justin. Thanks to the organizers. Right, so hang on. Here we go. So let's start with G, a compact Lie group, and alpha, a class in H3 of G with coefficients in U1. Okay, so now depending on your background, you maybe thought of different fun things that I might do with this data. And also depending on your background, maybe I should have called alpha lambda, because it's a level. So here's a list of some of these fun things. Maybe you thought about Chern-Simons theory, twisted G-equivariant elliptic cohomology, string structures, equivariant gerbs, orbifold actions on B fields, higher representation theory, and so on. So this list is not supposed to be like a prerequisite list for this talk. It is fine if you don't know about any of these things, but if you do know about at least one, it's something to keep in mind throughout the talk. We're not going to focus on any of these. We're going to focus on a final point, which is a smooth two group that I'm going to call curly G, associated to the data of G, U1, and alpha. And we're going to study its moduli space of principal bundles. This is also not a prerequisite for this talk. This is the content of at least the first half of the talk. And the reason that I pulled up this huge list of things is that there's a vague expectation that all of the above topics are related to this moduli space. So if you don't care about any of these topics, that's fine. For the purposes of this talk, you can just learn about this space. But if you care about at least one of these topics, maybe that can be something that you're keeping in mind as we go, about whether any of the formulas or ideas that we're seeing in studying this space are things that you've seen in studying your preferred topic here. So, of course, all of these above topics can be hard or abstract, and this makes it challenging to relate them, especially when they're sort of abstract in orthogonal directions. And so to make things slightly simpler to begin with, we focus on the case where the group G is finite. And in that case, we can study the space of this moduli space of G bundles concretely and show that it has nice properties. And this allows us to make explicit and concrete connections to this list of above topics and between these topics. And so this will be the first part of the talk, and this will be the last part of the talk. This is joint work with Daniel Berwick-Evans, Laura Murray, Apurva Nakade, and Emma Phillips. And I say that we started with the case where G was finite. And when we started, we really thought that we were working with a toy case and we might get some ideas, but that the general case of a compact group would be a huge step. But actually, now that we've proceeded, a lot of our results work with small modifications. And we have a lot of ideas about how to generalize the steps that we need to do. So we've actually learned a lot about the general case as well, although I mostly won't be talking about it today. Okay, so let's fix the following input data for the rest of the talk. We're fixing a finite group G and a abelian group A. So earlier I talked about coefficients in U1, but for most of the talk, we can take any abelian Lie group. And alpha is going to be a 3 cocycle. So this is a representative of our third cohomology class that we talked about earlier. So it's a map from G3 into A. And I'm going to be talking about cocycle conditions a lot throughout the talk without ever being explicit again. So let me just for once write down an actual cocycle condition. So D of alpha is a map from G4 into A. So it takes 4 input values, G, H, K, and L, and it's defined as this alternating fraction here. So just to give you an idea, we might start with H, K, and L, and we apply alpha to that. And now G appears in the picture, multiplying the H. And now the H bumps over and multiplies with the K bumps over and multiplies with the L, and the L goes out of the picture. So you can generalize this kind of formula to define n cocycles for any n. And so this should be equal to 1 as an element of A for no matter what 4 values of G you plug in. All right, so that's our input data, and we can now proceed with a plan for the talk. So I'm going to begin by defining smooth two groups and giving some examples. I'm going to define bundles for smooth two groups. So we're going to give definitions and some key results about the moduli space. And then I'm going to return to this original list of topics and see how it relates to this space that we've studied and how we can make connections between them. So that is the plan for the talk. And as Justin said, you should feel free to put questions in the chat or ask to be unmuted and ask away. All right, so let's start by defining smooth two groups. And we'll start with definitions and examples. And so I'm actually going to start with an abstract two group. And then a smooth two group will be like adding the Lie, making a group into a Lie group. So adding topology and geometry. So an abstract two group, denoted by curly G, is a monoidal groupoid in which all objects have tensor inverses. So it's a groupoid, meaning all morphisms are invertible. It's monoidal, so we've got a tensor product. And for every object, we can tensor it with some other object to get back our unit, our monoidal unit. So our first example of a two group is just an ordinary group. It's kind of a boring example. So let's start with H, any group. I changed the letter from G to H because here it's definitely not important that it's finite. So we make it into a groupoid in the ordinary way that we make sets into groupoids. We've got the objects are the elements of H, and we only have identity morphisms. And now, because we started with a group instead of a set, we make it into a two group by defining the monoidal structure of two objects H and K to be the product HK. So ordinarily, to define a monoidal category, we need to talk about associators and compatibility conditions. But because we only have identity morphisms, our associators are obviously also the identities. So that's our first example of a two group. Our second example is also pretty familiar. So now we start with an abelian group, and we make it into a groupoid with one object in the same way that we make groups into a groupoid with one object. So the automorphisms of our object are A, and composition is given by the group operation in A. So you can do this for any group, but we start with an abelian group. And so now we can also make this into a monoidal category. So obviously, when we tensor point with itself, our one object, we have to get back that object. But now when we tensor morphisms, we should get another morphism from our one object to itself, and that we use the group operation in A again. So here we're using the group operation in A to define two different structures on this category. And so it's an Ekman-Hilton sort of argument that the group operation needs to be abelian for this to work out. So that's our two group. And so we've seen two big examples here. One is where the objects have a group structure, and one is where the morphisms have an abelian group structure. And so finally, we're going to get to maybe an interesting example where we combine this. And so now we go back to our input data where G is finite, A is our abelian Lie group. The Lie group structure doesn't matter here that much. And alpha is a 3-focycle. And we define the category whose objects are the elements of this group G. And morphisms between G and H, we have no morphisms if G and H are not equal, and we have a copy of A if G is equal to H. So again, the automorphisms of each object are a copy of A, and we compose automorphisms using the group operation in A. Okay. And now, because our objects are a group, we can do the same thing that we did in example 1 and define G tensor H to be the object G times H. But because we have an interesting set of automorphisms instead of just the identity, in order to make this into a monoidal category, we must specify an associator. And there's lots of ways that we could do it, but our data alpha is exactly what we need. So we need an associativity morphism between the tensor product of G and H with K and the tensor product of G with H tensor K. And we know that from this definition that as objects of our category, these are both GHK. And so we need an element of A that gives an automorphism, and we can exactly apply alpha to these three elements, and we get our desired automorphism. Well, associativity morphisms in a monoidal category should satisfy the Pentagon axiom, which I'm going to draw on the next slide. So for many of you, this will be familiar, but for those who haven't, the important thing to see is that over here, we have four objects, G, H, K, and L, tensored as far to the left as we can. And over here, we have four objects tensored as far to the right as we can. And there are two ways of moving the brackets around using our associator. The Pentagon axiom says that these two ways should be equal. So going around the three-step direction, we get these three elements. And remember that composition is given by multiplication in A. So I haven't written composition symbols here. I've just gone ahead and taken the product in A. And over here, I've got two terms. And this is exactly the cocycle condition on alpha. So a 3 cocycle is exactly what we need to define the data of an associator for a monoidal category with objects G and automorphism A. All right. So that's our favorite example of two group. And it gives an example of what's called a finite two group. So that's a two group which has finitely many isomorphism classes of objects. And among finite two groups, it's a theorem that the ones that we just discussed are basically all of them with a slight twist. So this is a theorem originally due to Sin, who was a student of Grothendieck in the 70s. And, but she didn't publish. And so it was written later by Aswin. So they prove that up to equivalence, all finite two groups can be constructed in this way, such that their objects are, the equivalence classes of objects are a finite group G. The automorphisms of each object is an abelian group A, and we have a 3 cocycle giving the associativity condition. Now, the one subtlety that I have shoved under the rug here is that the abelian group A could have a G action, could be a G module, and in that case, our composition and we need to consider this G action rather than just taking products in A. So, but we don't use that in our work because we're interested in the trivial A module or trivial G module U1. But I just want to acknowledge that there is something going on here. And one way to think about this classifying data is in terms of extensions. So we saw that point mod A is one of our first two examples of a two group. And the G that we just defined fits into a short exact sequence of two groups where we have the boring two group with no morphisms, G, and we have the two group with only one object, point mod A, and in the middle, we have our curly G. And so we view curly G as an extension of G by point mod A. And we can show that this short exact sequence splits exactly when the cocycle alpha is a co-boundary. And we can also show that isomorphisms between things that you could put in the center here with identity maps for the point mod A and the G, those correspond to two cocycles, to two cochains showing that the cocycles are cohomologous. So in other words, just as A extensions of G, so an extension of a group G by an abelian group are classified by second cohomology, you can show that point mod A extensions of G are classified by third cohomology. Usually we talk about central extensions of groups. And here, the extension will be central exactly when A is a trivial G module. Okay, so in other words, all finite two groups fit into this framework of extensions, and they are all classified by cohomology classes. And so the point of this is that by restricting our study to groups of this type, we're not really restricting. It's not that much of a restriction. Okay, Here's an example of an extension which is not finite, but it is important and can be related to our examples. This is due to Chris Schomer-Priest, who explained that we can view the string group as an extension in this way. So if we look at spin n, for n at least 5, and we look at H3 with coefficients in U1, this is isomorphic to Z, and we choose a generator and a representative alpha string. And so Chris tells us that we should look at the 2 group defined by this central extension corresponding to alpha. And this is what he calls string n. Now, we know that if we, from the previous discussions, we know that if we choose a different representative of the same generator, we'll get an equivalent group. But what if we choose -1 instead of +1, for example? Chris shows that abstractly we get an equivalent 2 group. It's not equivalent as an extension because we have to apply an involution to this point mod U1. But abstractly, we have a uniquely defined up to equivalence 2 group called the string group. So before Schomer-Priest's work, we had other models of the string group as a cover of the spin group that were not 2 groups. They were ordinary groups, but they were very infinite dimensional and hard to study. So we do a trade-off here. We start working with morphisms and associators, and nothing holds up to, on the nose, it only holds up to equivalence, but on the other hand, it's a finite dimensional model. Okay, so obviously it's not a finite 2 group, but we can, starting with a representation of a finite group, G0, let's call the representation rho naught into SON, we can form a finite 2 group of the class that we study. So here's my representation. And then I take spin covering SON and I pull back. And so what I get is a Z mod 2 extension of G0. And that's what I'm going to call G. And I have a spin, a representation row here. And now I do this again, but now I've got a 2 group. So string n living over spin n, and I'm going to pull back G along that map. And I get a 2 group, which is a point mod U1 extension of G. And we've just discussed that point mod U1 extensions of G are classified by 3 cocycles. And what is that 3 cocycle? It's the pullback of alpha string, a cocycle here, to G.
So Emily, we have a question, which is, can you elaborate on the definition of a central extension of a 2 group?
Yeah, so I want my morphisms. So when we have a monoidal category, we can tensor objects, but we can also tensor morphisms. And so I want both of those things to land in the center. So let me draw here, maybe. So I have point mod A landing in G, landing in G, and I can define in here a center. And this is going to be objects that commute. And probably for this, I just want, so for an object to commute, I should give a bunch of isomorphisms that show that it commute. But I think to define a subset of the objects, I'm just going to talk about the objects such that there exist morphisms that make it commute. And so that's a little bit of subtlety. But in this case, we definitely know that the object point is going to go to the identity. So that's definitely going to be in the center, however we define it. And morphisms, we want the property that Z tensor A is going to be the same as A tensor Z. So it's what you imagine. So this contains a center. I'm not writing very well. And we want this to land in the center. So it's very analogous to what we want for what we define for classical groups. Does that answer the question?
He says yes.
Okay. All right, so that's what a two-group is. And now we want to make a smooth two-group. And so we want that our objects and morphisms should both form manifolds. And so the way that we do this is we define a group object in the bicategory of smooth stacks. And our category of smooth stacks looks like this. Our objects are Lie groupoids. Our one morphisms are bibundles. And our two morphisms are isomorphisms of bibundles. So if you're not familiar with bibundles, this is totally fine. I will not say very much about bibundles or use very much about bibundles throughout the talk, but I just wanted you to get a feeling for this. And so because we're working in a bicategory, when we have multiplication maps and things like that, we don't expect group axioms to hold up on the nose. We expect them to hold up to specified two isomorphisms, which in turn should satisfy compatibility conditions. So it's very analogous to the associators that we saw and the Pentagon Axiom that we saw as well. And so all of our examples fit into this framework. And they're not maybe hugely exciting as Lie groupoids. The objects are going to be discrete when we have finitely many of them, but the morphisms have some topology coming from the topology of A. Okay, so those are our smooth two groups. And now we want to say what is a principal bundle for a two group. And so for the beginning part of this section, we can work with any smooth two group. It doesn't need to be finite. It's only when we get into classification questions that we use our finiteness assumption. So let's fix our smooth two group and a smooth manifold. And our goal is to define principal two group bundles over X, and they should form a bicategory. Now, there's many ways to do this. First of all, based on analogies with the classical setting, and also based on infinity category theory, and so which is correct. So for example, in the classical setting, you can define bundles in terms of classifying spaces and maps into classifying spaces. You could define bundles in terms of locally trivial things with transitive actions. You could define, you could work with flat two bundles when you're in a finite group situation. All bundles are flat. And you could talk about the holonomy. And so at first we didn't know which of these to take and whether they would be equivalent. And in the end, we eventually settled on a favorite approach, and we showed that it reduces to all the others. So any of them are correct, basically. Another approach we could have taken is we could pull out our copy of Lurie and say, aha, we have infinity groups and we have infinity bundles, and so let's just truncate. And we didn't want to do that because we are in a very concrete setting, especially with our finite groups, where we can be very hands-on and explicit about our higher compatibilities. And so we wanted to take advantage of that rather than just using the biggest canon that is available. Okay, so let me tell you our favorite. So it's going to be a smooth stack, P over X, equipped with a G action, which is locally trivial, meaning that there's a surjective submersion from Y to X, and an isomorphism of G stacks over Y when we pull back P to get a stack over Y, and we look at the trivial G bundle, Y cross G. So if I just changed the font from curly G to ordinary G and remove this word stack here, this looks exactly like the definition of an ordinary G bundle. But I just want to highlight that there is more data here, because what is a G action? It's first of all a map of stacks, P cross G to P, but it's also an isomorphism, so a two-morphism, that show that we have a unit condition and we have an action. So there's extra data there, and there's also extra data here, because to be an isomorphism of G stacks, you need to satisfy an equivariance condition, and it's not a condition anymore, it's data. So I just want to highlight that there is a little bit of extra data in the background here, and what we end up doing is unpacking this data in the special case of a finite group. Okay, so how should we unpack this data? Well, the first thing we observe is that we have a forgetful functor from these curly G bundles to ordinary G bundles that just come from taking isomorphism classes everywhere. And our theorem, our first theorem, is that this is a torsor whose fibers are each copies of A gerbs on X. For those who don't know what gerbs are, I'll be discussing them in a couple of slides here. But the idea is that this is a symmetric monoidal bicategory, and it acts on this total space here. And each of the fibers are copies of this bicategory. And so this tells us that sort of non-canonically, to define a curly G bundle, we need an ordinary G bundle plus some kind of gerb data. We can be more specific about that. So how do we prove this? We use a Cech style reformulation of the bicategory Bun-G. So what I mean here by Cech style is that I choose a cover where everything is trivial, and I look at the data for patching things together. And then because we're in a higher categorical setting, I need to look at compatibility conditions over triple intersections and so on. So let's discuss that now. So we know that P is locally trivial. So we choose a surjective submersion over which it trivializes, and we fix a trivialization, which is called D. And then very similar to the classical setting, if I pull back to the fiber product y cross x over y, I obtain two isomorphisms. So I can pull back in two ways, and I obtain two isomorphisms between the pullback of P and the trivial bundle. And composing those, I get an automorphism of the trivial bundle. And it should satisfy a cocycle condition when I pull back again to the triple product, which looks like this, that pulling back, there should be a star here. So pulling back along the first and third projections is the same as first pulling back along the second and third and composing, pulling back along the first and second. So far, this looks exactly like the classical story, except that in the classical story, this is an equality. In our story, these are bibundles. Okay, so these are one morphisms in a bicategory, and I want a two morphism saying that they're isomorphic. Now, this is the one thing that I'm going to use about bibundles, is that a bibundle is in particular an A bundle over a certain base space coming from the domain. And we want to refine U until we can trivialize that A bundle. So that's fine. We refine U and we fix the trivialization of the A bundle underlying gamma. And then eventually we discover that we associate with P a triple of this refined submersion, rho, which is a map from the double fiber product into G, and gamma, which is a map from the triple fiber product into A, basically coming from this trivialization. And these should satisfy certain cocycle type conditions. Okay, so that's the kind of Cech data that we get out from P, and we can do a similar analysis for morphisms between principal bundles and two morphisms. Okay, so now let's go back to the theorem. Now we want to show that this fiber of this map pi from two group bundles to ordinary group bundles looks like a copy of the category of gerbs. So what is a gerb? Well, in light of our definitions, we can think of a gerb as a principal point mod A bundle over X. And so let's go back a second to our classification here. So it's going to be classified by three pieces of data, but now we have that G is equal to point. So this data is not interesting, and we just have U and gamma. So in other words, an A gerb can be determined by a surjective submersion and a Cech 2 cocycle. Similarly, an A2 gerb is determined by a surjective submersion and a Cech 3 cocycle. So that's just a shift in the index. And so now we can prove the theorem. So first of all, given the data of G and alpha, So this is our initial input data, no bundles yet. If we start with a principal classical G bundle, we get a 2-gerb on X unique up to 1 isomorphism. And so one way to think about it is to associate to P check data. And so it's an ordinary bundle. We just have 2 pieces of data. We have U and rho. And we obtain a 3 cocycle by pulling back alpha. In other words, so lambda P should take in 4 values, y1, y2, y3, y4. We apply rho to each consecutive pair, y1, y2, y2, y3, y3, y4. So we've got here 3 elements of G. And we can apply alpha to that, and we get an element of A. And now you can argue using the nice property that rho satisfied and the nice property that alpha satisfied that this lambda P is a 3 cocycle. Okay, so now let's look at the fiber of pi over P. So we want to look at principal G bundles, curly G bundles, whose underlying G bundle is the bundle P that we just looked at. So we associate to P the check data U, rho, gamma. And here, probably I should have done this first so I could choose a compatible U and rho. So remember that before defining gamma, we had to refine U possibly. Okay, now we can study the category of 2-gerbs, and we can see that the data of gamma, here that's the only additional data that we needed to lift ordinary P to curly P. The data of gamma is equivalent to a trivialization of this 2-gerb. And so the fiber over P is the bicategory of trivializations of this 2-gerb. And then it's not hard to see that the bicategory of trivializations of this 2-gerb is non-canonically isomorphic, equivalent to the bicategory of gerbs. So that's a sketch of the proof. Are there any questions so far?
Doesn't seem to be.
Now, I mentioned at the beginning of this section that maybe we should have defined 2 group bundles in terms of classifying stacks. And so what if we had done that? So first of all, how do we define B of curly G? We define it to be this pullback. So alpha gives us a map from BG to B3 of A, and we pull back point along there. And so we get something that we call B of curly G. And if this is a good definition, we expect principal G bundles to be classified by maps from X into this space. Now, to give a map from X into this space, I should give a map here and a map here, which is no data. That second piece is no data. And I should give something that makes this diagram commute. In other words, this composition here is the trivial map. And this composition here will be something. And this should be a trivialization of it. So in other words, a map from X to B curly G is the same thing as a map rho from X to BG together with a trivialization of the composition. Well, rho is a principal G bundle. And this composition corresponds to a 2-gerb. And so this is exactly telling us that a principal G bundle is determined by a principal ordinary G bundle together with the trivialization of the corresponding 2-gerb. And this is exactly what we just found using our more geometric definitions. This is a more topological homotopy theory definition. So that's why we didn't choose this as our main definition, but we observed that it's consistent. Okay, now let's talk about the special case of flat G bundles and holonomy. So our definition of a flat G bundle is a principal G delta bundle where we give the discrete topology to both the objects and the morphisms. And recall that in the classical case, flat ordinary G bundles are classified by homomorphisms from pi 1 of X into G. And so our theorem is that when X has contractible universal cover, flat principal curly G bundles are classified by homomorphisms of 2 groups from pi1 of x into curly G. And here pi1 of x is an ordinary group, and we saw early on that we can view it as a 2 group in a boring way. And I'll explain in a minute that why we have this notation here, rho and gamma. So actually, rather than just studying homomorphisms of 2 groups, what we really want to study is functors of bicategories from point mod pi1 to point mod G. So let's again go back to the classical case of an ordinary group. A functor from point mod pi1 to point mod G is just a homomorphism, which we call rho. And we want to lift this functor so that it actually lands in point mod curly G. And we need one extra piece of data, which is a map gamma from the product pi1x plus pi1x into A. And why do we need that data? This data provides isomorphisms that rho 1a times rho 1b is isomorphic to rho 1a to rho ab. And so to give a map into a 2 group, you don't just give a map, you give something that shows that it's a homomorphism. And so that's what gamma is doing here. And it should satisfy this condition. D gamma is equal to 1 over rho star alpha. And this notation is kind of reminiscent of the fact that in our Cech description, we also had a gamma that was giving a trivialization of rho star alpha. Okay. Now, what about morphisms in this category? So if we have 2 functors in the classical setting, rho 1 and rho 2, then a natural transformation is given by an element of G that conjugates one to the other. In other words, T times rho 1a is equal to rho 2a times T for all A. But of course, to lift, we need something that shows us that this is equal. We need an isomorphism there. So we need an eta such that eta of A gives us that isomorphism for each T, and it should satisfy also some cocycle condition that involves rho 1, gamma 1, rho 2, gamma 2, and alpha. And finally, 2 morphisms. Well, in the classical setting, we don't have 2 morphisms. And in this setting, we only have 2 morphisms between actual things that are actually already equal. But we do have more than just the identity 2 morphism. We have a copy of A. Okay, so that is a bicategory. And we can identify that bicategory in the case that X is a K pi 1 with the bicategory of flat principal curly G bundles. And this identification is clearly compatible with the classical identification of a flat G bundle with its holonomy. And we also recall that this category here has a nice simplification or nice presentation as an action groupoid. So we look at group homomorphisms from pi1x to G, and that has an action of G by conjugation. And so giving it this presentation means that we can understand the morphisms very well. So we prove that this action of G downstairs lifts to an action of G on this bicategory upstairs. And this gives pi the structure of a cloven 2 fibration. So maybe this is a fancy word, but if you think about what you know about fibrations, you've got a lifting property that if you have 2 objects downstairs and a morphism between them, and 1 object upstairs, you can complete this diagram. So you can lift to a morphism upstairs. And since we have this nice presentation here, all morphisms downstairs can be viewed as an element of G acting from the target, from the source to the target. And so giving an action of G upstairs allows us to say what the morphism should be that we lift to. And so not only do our morphisms exist, we provide a compatible set of choices, and that's a cleavage. Any questions at this stage? Right. So let me say a little bit about the action.
You got one. You got one.
Excellent.
So should we expect bun gx to be hom pi 2x to g?
No, we should not. Right. So we need, in the classical case, first of all, we need the flatness, although for finite groups it's not important. And we have this action of g that is important. I did have.
Right, I think g is supposed to be a.
Or two group. Yeah, no, we don't. We want to work in the bi-category level, not with the monoidal categories. The morphisms are a bit different. And I did have this condition on the universal cover of X, and we think that you can remove this condition, but you should not work with the fundamental group. You should work with the fundamental groupoid. Okay. So to give an action of a group on a two group, we need to define autoequivalences for each element of G that give us the action of that element G. And so we can do this. And for example, on objects, we're lifting the action already downstairs, so we know what it has to do to rho. We know that it has to conjugate rho. So here's our rho G. And what I've done here is I've written brackets. And as an element of G, obviously the brackets don't matter, but having a choice of brackets in here allows us to see what gamma G should be. And I just want to explain that quickly. So gamma G of AB is supposed to give us an isomorphism between rho G applied to A times rho G applied to B and rho G applied to AB. So I need to give an isomorphism between this expression and this one. And because I've got my brackets in, I can see that there's a way to move the brackets around using associators until I get G and G inverse next to each other. Then I apply the fact that G and G inverse multiply to 1. And I move the brackets around some more until rho A and rho B are next to each other. And then I use my original gamma. So this is some complicated formula, but that is motivated by where we put brackets to begin with. If I had bracketed to the left instead of to the right, it would be fine as long as I'm consistent. I would get something equivalent. So anyway, we get an explicit formula. We check that it satisfies d gamma is equal to 1 over rho star alpha, and so on. So we just keep defining all the parts of this functor fg, which is a functor of bicategories. And we also show that it gives an action. So fg composed with fh is equivalent to fhg, and we have higher isomorphism and so on. So this action is very concrete and explicit, and that's something that we can do in the finite group case. All right. And so at this stage, we've got our bicategory of two group bundles and a flat two group bundles. And we have a nice functor that we understand to ordinary two group bundle, ordinary bundles for the original underlying group. And we know that this is a two fibration, and we understand that the fiber looks like gerbs. So let's see how we can relate this to some of the topics that I mentioned at the very beginning. So let me give a lightning introduction to the Freed-Quinn line bundle. So we fix G a finite group, and from now on, A will be U1, and we let alpha be a 3 cocycle. So Digraph and Witten studied Chern-Simons theory for this finite data briefly, and then Freed and Quinn studied it at more length. And they construct a line bundle L on the moduli space of principal G bundles over Riemann surfaces. And it has the property that if you fix a Riemann surface, you look at the line bundle on the moduli space of G bundles on that surface, and you look at the global sections, that is the vector space that Chern-Simons theory assigns to the surface X. So this line bundle knows all of the two-dimensional information. We can also study this in the special case of only elliptic curves. So we look at the moduli space of principal G bundles over elliptic curves. Let's call the line bundle there L1. And Nora Ganter shows us that this line bundle is the home of twisted G equivariant elliptic cohomology. So these are some of the topics that appeared in our earlier list. And how is it related to our discussion? Well, we show that the two fibration, sorry, guys, can you be quiet? So the two fibration categorifies the Freed-Quinn line bundle. And what do I mean by that? Well, we saw that it's a fibration whose fibers look like gerbs. I guess they're flat gerbs, no? U1 gerbs on X, and we take isomorphism classes of the fibers, and we know that isomorphism classes of gerbs are given by H2 of X with coefficients of U1, which is just U1. So when we take isomorphism classes, we obtain a principal U1 bundle over the moduli space of D bundles on X. So this U1 bundle corresponds to some line bundle, and that line bundle is LX. Now, okay, for a finite group, this contains finitely many points, but what's interesting is that the isomorphism is compatible with the G actions everywhere. Okay. Now let's see how this relates to string structures. So in the special case that G is a two group arising from a representation. So remember, we started with our finite group mapping to SON, and we pulled back twice to get curly G. We can talk about spin structures and string structures. So if we start with an oriented vector bundle with structure group G0, then a spin structure is a lift to a G bundle instead of a G0 bundle. And in light of this nice presentation of string N due to Chamorro-Priest, we can say that a string structure on P should be a lift to a curly G bundle. Now, on the other hand, people have been studying string structures since before we had Chamorro-Priest's construction. And so we had to come up with other ways of saying this because we couldn't lift to a two-group bundle. That didn't make sense. So I have two other approaches that other authors took. So here's an approach due to Waldorf. So he says, let's start with a principal spin bundle. A string structure on P, he says, is a choice of trivialization of the two gerb that we saw, which is determined by P in the 3 cocycle alpha. So Waldorf came up with this definition about 10 years ago, and Chamorro-Priest's presentation is almost the same time, 9 years ago or so. But until this time, nobody has explicitly compared these things. But in light of our fibration, it is immediately obvious that the string structures definitions coincide because the fiber of bun-G over P, so lifting P to curly P, is exactly the same as choosing a trivialization of this two-gerb. So this just falls out immediately that and this is, I don't know, this is impressive to me because how did Waldorf come up with this definition without having access to the string group? But it's exactly the right thing. Okay, here's another approach to Stolz and Teichner. So they start with a principal flat G bundle, and they consider Chern-Simon's theory for P. I'm going to call that CSP. And they say that a geometric string structure on P is a trivialization of CSP. So in particular, if we look at two manifolds, and so we have a nice map F from a two manifold M to X, then CSP assigns to that map F a line. And if we have a trivialization of CSP, we should have a compatible choice of points for all of these lines. But we have proven that this line is the isomorphism classes of flat curly G bundles living over F star of P. And so if we choose a flat lift of P itself before pulling back, then we can pull that back along any F and we'll get compatible non-zero points in each line. So in other words, it's easy to compare part of the data of the trivialization of CSP, namely what it does to two manifolds, to part of the data of curly P in the fiber, namely its isomorphism class. So kind of an obvious question is, well, there's a lot of data that we forgot about here, and there's a lot of data that we forgot about here, and can we also match those up? So trivialization of CSP for all dimensions and the bicategory structure that we truncated to produce Freed-Quinn. So that is work in progress. And that is all that I want to say. So thank you.
Okay, let's thank the speaker. Okay, any questions? Let's see. Okay, we've got one.
Go ahead.
Yeah, hi.
Hi.
So, yeah, can you just go back to the slide where you had that condition with the contractible cover?
Mm-hmm. Let me see.
I didn't get it.
Sorry, I have a lot of slides.
Oh, right. So yeah, so I was asking it here. So if I have, I thought intuitively flat principal curly G bundles would be classified by maps from pi to pi, I don't know, pi less than or equal to 2 of x to G.
Yeah. So, yeah, that's what we think also, but we haven't worked it out.
Oh. Okay, that's what I was asking. Okay.
Yeah. So the reason it's much easier in this case with contractible universal cover is that we can always take our U to be just the universal cover. So we don't need to worry about refinements or anything like that. And so it just falls out. But that we think that that's what would happen. Yeah.
So this considers all cases with the G bundle where there is the action of the G on A, right? The general case.
No, we haven't considered that at all.
Oh, okay.
Yeah.
Okay. Yeah. Thanks.
Okay, do we have any other questions?
I have a question, if it's okay.
Go for it.
So, presumably, I wonder if it would be possible to tell sort of a similar sort of story using higher co-cycles, where you consider maybe not two groups, but three groups or higher, which are realized by this sort of higher extension. Do you expect that the same sorts of results about like the sort of geometry of these moduli spaces of bundles will be true?
I mean, people say this in introductions of papers, right? But we have not thought about it at all. So I don't know that it, like we were just kind of surprised by how concretely we could do everything, you know, that we could actually define an action on a two category, not just by like pull back and it works, you know? Yeah, so.
I mean, a sort of a slightly different question is, so your construction, so I guess it took place in the smooth category entirely, but one could have, I guess, also imagined working in terms of algebraic geometry and studying algebraic, like these constructions like internal to algebraic stacks. Again, do you think the same sorts of your theorems will still hold in that setting? Is there something special about the smooth category?
That's a good question. Yeah, I don't know. I don't know what would go wrong, but I have not thought about it at all.
Thanks.
Okay, great. So do we have other questions? Let's see. Hand is raised. Okay, so we've got another one.
Yeah, again, hi. Another question. So in from the start, you said like the underlying group, the object group was for the most of the cases we took it as a finite group, and the abelian group was U1, right? Or we could take any finite abelian group also.
It didn't need to be.
Okay. So so that A group basically. So the thing is that if you're thinking of quantizing, or if you're doing the Dirac-Fitton theory, ideally we will need the Dirac-Fitton theory, if the abelian group was finite, we would know how to quantize it. But if you replace it with U1, what happens? Do we know how to quantize?
No. Nothing to add.
Okay. Okay, thanks.
All right. So any more? Okay, looks like that's all the questions. So if we would thank the speaker again.